Okay, thank you.
Okay, good afternoon, everyone. This is Jackie. I am an application engineer from Cybernet Systems. Today, I'm going to show you the vehicle controller design and testing with hardware in the loop technique. We'll have a QA section after presentation. Please hold your question until then. Let's start from the agenda. First, I'm going to introduce you model-based design. I will give you a few concepts about modeling and simulation and suggest you what kind of tool you will probably need. After this, we will be interested in how do we build a vehicle model. Lots of vehicle model functions can be used. Which one is better? How can we test with vehicle model will be introduced with the hardware in the loop section. In this section, I will use example to explain why we need hardware in the loop. Finally, I will show you some success stories by using simulation tools and hardware in the loop technique. Let's get the ball rolling. Let's take a look on model-based design. Before we start this topic, I would like to ask you why we need simulation. Vehicle testing institutes have started testing and validation for almost 60 years or more. From Europe to America, all the testers face a serious fact. Vehicle testing is dangerous and expensive. As you can see, if you crash this truck in real world, you might spend over $150,000 US, not include the test driver and the crew. Therefore, the requirement is coming. We can't afford this kind of expense, but testing is important to evaluate the vehicle performance. Can we do some simulation before real testing? That is why we need model-based design. So, model-based design is a method. This method is used in controller development and testing, which is based on the response of a planned model. It also be used in various kinds of industrial fields, such as aircraft, power grid, vehicle, battery, and so on. Model-based design is useful for product evaluation, system integration planning, controller design, and development. We can say that everything in the world can be a planned model. Now, we have a new name, planned model. I will explain you what is planned model in next slide. So, what is the planned model? I could assume that everyone here knows that force equals to mass multiplied acceleration. If I put a force on a mass body, it will have a specified acceleration. That mass body is our controlled planned model. We can say that if the model is accurate enough, we can know the acceleration value in any time. We can develop a controller to control the acceleration, which is based on the mass equation. Let's make the problem more complicated. The F equals to NA is not how the real world works. The real world is more complicated. We have friction, damping, and other mechanical parts. If our background knowledge is strong enough, we can still make the plane model as a transfer function, or you can say state space function. For example, force is equals to nx double dot plus bx dot plus kx. you can get the transfer function by Laplace transform. This transfer function is going to be used when we want to develop a controller for it. The question is, we have to know the condition very well in order to build up the model. Let's summarize what we have known now. We introduced the concept of model. A model is a digital twin from a real target. It will respond as a real object. A model is built by our domain knowledge. If we want the model response more like a real one, we have to consider more details. A model should act as the real target. Therefore, we can develop our control algorithm. A model should also feedback signal we want. It means that the model should have the details. For example, if we want to know how much force should I use to make the mass body move with one gravity acceleration and 0.8 friction, I must include friction parameter in my model. So in conclusion, development based on the model is called model-based design. So after we learned about the model and model-based design, I am going to show you about the vehicle modeling. We have learned about model and model-based design. The most important thing in modeling is the domain knowledge. So how about the vehicle model for model-based design? In vehicle dynamic modeling, we will probably use some simple model. For example, 2 degree of freedom vehicle model, 3 DOF vehicle model, and a multi-DOF vehicle model. Let's start from the 2 DOF vehicle model. This vehicle model is a simple vehicle model, linear and ideal. The only variables are the lateral speed and yaw rate. You might find some papers which is building control algorithm based on 2 DOF vehicle model. Keywords like direct low moment control, chassis control, and four-wheel steering can help you find this model. This model is good, but not good enough. Let's take a look on 3 DOF model. This is the 3 DOF vehicle model. It's better because we have longitudinal speed. We can have some powertrain control on it. However, it is still ideal. We don't have some suspension details in this model. Although it becomes nonlinear, it is not the model we want in the end. So, the goal is much farther than we can imagine. We have to think about the suspension system, the brake system, and the steering wheel system. If you haven't get lost here, we still have tire model, suspension kinematic and compliance, and aerodynamic. There are lots of details in vehicle model. They can be easily put into the multi-DOF vehicle model. More detail means more simulation time with lots of nonlinear parameters. In the same time, more details means you have to complete know about vehicle. That is the hardest part. Lots of people will say that this vehicle model is too complicated for me, except for the specific model I want. However, we can say that if your background knowledge is strong enough, you can build your model in this way. And in the next slide, I will show you a different modeling method. The modeling method I have showed you before is based on math function and pure calculation. It is fast, but the accuracy depends on the completeness of the model. If our domain knowledge is not strong enough, we will probably get a non-accurate model. This method is usually used in system-level design. The other modeling technique is finite element model, which is using CAE simulation tool. The idea is separating the model to finite meshes and simulate each mesh's response. CAE simulation can have a high accuracy. However, the trade-off is simulation time. Generally, we will spend tons of time to simulate one part of a vehicle. We will probably use this method when highly nonlinear part in the system is concerned. Let me use a graph to explain this for you. In this graph, the x-axis is the simulation time and the y-axis is the simulation accuracy. We have 2 DOF and a 3 DOF model, which is fast but not accurate enough. The multi-DOF is accurate, but we have to spend more simulation time. CAE simulation is the most accurate technique with lots of simulation time. We can also find that the relationship between simulation time and the accuracy is not linear. One little improvement in accuracy might cause 10 times of simulation time increasing. The question is there any method that can simulate with high accuracy and short simulation time? The answer is yes. The answer for the accuracy and the time is modeling by lookup table. The lookup table is built by experiment and simulation result. That help us to implement nonlinear and complicated model. This kind of model is also called black box model. As you can see, we can build an engine model by table. The table will determine that how many torque the engine will output at current throttle position and engine speed. In this table, we do not concern about the design of engine, the volume of engine, or the architecture of the engine. All we want to know is the performance of the engine. With this model, we can have a higher accuracy with short simulation time. The only question now is we have to build a complete architecture of the plane model first. We need domain knowledge. However, some simulation tools have helped us to conquer this problem. CarSim is one of the simulation tools that can solve this problem. It has model architecture from chassis, powertrain, brake, steer, suspension, tire, and aerodynamics. All we have to do is import the parameter of our target vehicle to CarSim to build the model. Also, user can use CarSim to build testing procedure and environment. You can design your own testing sequence in CarSim with your vehicle model. Now, we know about the vehicle model well. In the next slide, I will use an example to help you understand about the system level and the component level. We take the transmission as an example. Assume that we are a transmission engineer. We will probably concern about the cost, the volume, the heat transfer efficiency, the durability, and the power efficiency. You will find that the performance of the transmission is the main object for transmission engineer. However, if we are a vehicle controller engineer, we will think about how can we get the gear state signal. Can I implement my shifting schedule? How could I receive the fault or warning signal? We will find that the whole vehicle performance is the main object we concerned. So here is a comparison between system level and component level. For transmission engineer, the object is component level development. The tools for component level design needs to have accurate simulation results for complicated conditions. CAE tools like ANSYS Mechanical is suggested. However, for vehicle controller engineer, the object is system-level development. The tools for system-level design need to have the whole dynamic of plane model. The behavior of target is much important than the details. Simulation tools like CarSim and TruckSim is suggested. We could find that we select different simulation tool because the requirement is different. After we modeling the vehicle, we have to do some calibration to make sure the model works as the real vehicle. There are a lot of calibration we can do. Generally, we use vehicle dynamic testing method. The method is used to check vehicle's spec and performance. It means that we can easily understand whether the vehicle model is accurate enough. We can also evaluate vehicle performance by the result of testing. Most of the testing sequence is open loop control. Open loop means we control the car without any kind of vehicle dynamics feedback. For example, full throttle instead of constant speed. Turn off the steering.
Hello, Jackie. Participants, we're sorry that we. Okay, Jackie. Hello.
Where should I restart?
Please start from this slide. Thanks.
Okay.
Thank you.
Sorry for the internet problem. So after we modeling the vehicle, we will have to do some calibration to make sure the model works as the real vehicle. There are a lot of calibration we can do. Generally, we use vehicle dynamic testing method. The method is used to check vehicle's spec and performance. It means that we can easily understand whether the vehicle model is accurate enough. We can also evaluate vehicle performance by the result of testing. Most of the testing sequence is open loop control testing. Open loop means we control the car without any kind of vehicle dynamics feedback. For example, full throttle instead of constant speed. Turn the steering wheel with constant force instead of specified angle. Full brake command no matter ABS is on or off. This kind of open loop control will prevent the response error from human control. The common vehicle dynamic tests include constant radius, frequency sweep steer, step steer, impulse steer, on center steering, straight line braking acceleration, and braking in turn. This kind of testing will help us know about the vehicle performance well. So in this slide, I will use a user case to show you how CarSim finds problem for your design. In this case, user use a unique steering system like recirculable steering system. This animation shows a recirculable steering system. The customer actually used a multi-link arm to control the steering angle. The relationship between steering angle to pivot arm angle is like this graph as a result of the multi-link arm. You can see that the relationship between steering angle and pivot angle is highly nonlinear. We help them to build it in CarSim and see what will happen. Okay, after modeling, we test this vehicle with the vehicle dynamic testing, static steer test with brake on. The procedure is that the vehicle is static with brake on, and we will rotate the steering wheel smoothly. Brake on will make sure that the vehicle will be static in the longitudinal axis, so that the torque in z-axis will have a bigger impact. You can see from this graph, the x-axis is the steering angle and the y-axis is the steering torque. A key point is the slope between steering torque and the steering angle. In vehicle dynamics, we call it steering gradient. The steering gradient will show whether the steering wheel is good to drive. As you can see, we have lots of rapid increasing or decreasing in steering gradient. This makes the vehicle hard to drive. For customer who is starting autonomous vehicle, this helps them find the problem. They knew that the steering system is very hard to control for their controller, but they never found that the problem is from the bad steering system. We help users compare to real target and find this problem, improve and solve it, help them reduce the time in the end. Another case is the Pirelli. Pirelli used CarSim to test about their new tire model. There are two testing procedures. Send distance to compare the fuel consumption. Send throttle command to compare the travel distance. We can imagine that if we want to test this in real world, we need two teams to maintain the vehicle condition, doing their best to make sure the vehicle shows no difference except for tires. In the same time, these two vehicles will always have some difference. For example, the engine will have difference since that the mileage is different. So, the testing environment cannot be always the same. Sunny, raining, dry, or wet can have impact for the testing result. All of these variables can be controlled in simulation. We can have a totally same vehicle except for tires in CarSim. The simulation difference is as a fully result of the tire model's difference. They use CarSim to save lots of human costs and vehicle maintenance to test their tire model. So, simulation tool can not only help you modeling and calibration your vehicle, but also help the controller design. Vehicle can be controlled by driver, controller, or both. We can use simulation tool to build different testing procedures. Run simulations with driver control, with controller, and lots of testing environment. This slide shows some vehicle control function example. As you can see, vehicle control function should get some information from vehicle, such as vehicle speed, wheel speed, and yaw rate. If you want to develop the controller, simulation tool should feedback these kind of variables to test your control algorithm. For example, ABS controller will calculate the brake command via the value of current vehicle speed and wheel speed. So let us take the ABS system testing as an example. We can overlap two kinds of simulation results with or without ABS controller on split friction road. Test and compare with different kinds of model will be easier and cheaper. We can use this to develop and tuning our controller with very low cost. This is how we build vehicle model and develop controller with simulation tools, quicker and safer. Now, we have a full concept of model-based design and vehicle modeling. We do understand that simulation can help us to develop controller. In the next section, I will show you about the hardware in the loop. The hardware in the loop, as known as HIL, is a controller design and testing method. Let's assume that we have a controller under testing. The controller has to receive some signal from a real car. For example, ABS controller will have to get the wheel speed from a real car. Then, the controller will calculate the control command and send it out. Just like the ABS controller will send out the brake control command. The different point is we will connect these signals, inputs and outputs, to a real-time simulation platform, which is running CarSim. Now, you might want to ask a question, why here? We could test the control algorithm in our computer. Actually, this kind of method is called software in the loop. The difference is here consider more about the communication and hardware performance. For example, what if the controller works worse than when communication rate is slower than expectation? What if our controller hardware have some faults and bugs? A real controller will communicate with sensors and other control units. It might receive data from VCU and generate commands to brake system. In different situations like high temperature, wrong connection to power supply, or receiving errors from other control unit, will change the behavior of your controller. This kind of condition will probably be happened when you test your controller in real car. HIL can help you solve this problem in early stage. The second question you might want to ask is how can HIL do that? First, HIL systems work in real-time OS, which can make sure the calculation rate is the same as real-time. Meanwhile, HIL box can support different kinds of communication input-output card. You might have lots of communication channels like CAN, LIN, digital input-output, and analog input-output. HIL box can help you to use this I/O without any delay. You can also set some simulated fault signals to test your controller. Last but not least, HIL box can decrease the time you spend on real-world testing. With the HIL testing, we can use a simulation tool to different kind of application field. We can develop autonomous vehicle by testing with ADAS controller via HIL method. With CarSim RT and the sensor module, we can develop not only ADAS but also autonomous controller. Vehicle dynamic controller testing and validation can be implemented with different kind of testing procedure. Chassis control, ABS control, or four-wheel drive control can be easily tested with CarSim. We can do simulation with very low cost and reduce the time we need for tuning and verification. We can also use simulation tool to do subsystem testing. Sometimes we will want to evaluate different subcomponents on the same car. For example, which brake system is suitable for my target? We can build different brake systems in CarSim and test with the same car. Now, we can say that we have known about the model-based design, vehicle modeling, and hardware in the loop. In the next slides, I will show some success story with you. The first case is the EPS system testing. For EPS controller, we must receive steering torque and vehicle speed to calculate the assistance force. In this case, we build the rear steering system with throttle pedals and connect them to real-time machine so that it can simulate with CarSim. Once CarSim gets the driver input, it will calculate the steering torque and the vehicle speed, send it to target controller. The target controller will control the assistant motor to fulfill the EPS system. Our controller use these to develop their EPS system. This kind of testing helps them easier to develop and testing. In the end, they also use this system to demonstrate to consumer, convince them about the performance. Another case is for vehicle design. They use CarSim's example as a template. CarSim have PBS testing procedure as example. Our user import their vehicle model and use it to test about the vehicle's performance. The interesting point in this case is the trailer. A tractor with trailer is very expensive. If there is any crash or accident in real-world testing, there will be an unbearable cost. However, we can test it in simulation to evaluate the performance of our target. And in this case, we use Bison RT, Opal RT, and Python to build up an automatic HIL testing. Since that Bison supports a component object model, which is based on Windows component, we use Python script to open Bison, load the model to target, and execute the simulation. As the video, I ran the Python script from command line in Windows. After a few seconds, the Bison software will be opened. Since this is an automatic testing, we can see that there is no need to use mouse or keyboard to set up the simulation. And the auto setup procedure is done. The simulation will start running. This kind of auto simulation is widely used for hardware testing. We can use Bison to build a full testing schedule, includes hundreds of testing items. For this case, it's also a HIL case. We use biasing RT, Oppo RT target to simulate a real bike. We also use NR2, which is a motor real-time simulator. In this case, we connect the real-time target to a real throttle handler and brake handler. Send the throttle command to the customer motor controller. The motor control unit will send the motor command to NR2, the motor simulator. Once the motor torque is sent to biasing, the bike in biasing will be driven and generated a vehicle speed which is going to be used to traction the motor. As you can see in the video, the engineer on your left-hand side will ride the bike. You can see the loading torque of motor on your left-hand side. And the virtual biasing bike is driven on your right. This is an EV powertrain system HIL testing. So you can see this is the current of your motor controller. This is the rotate speed and the condition of DC bus. Okay, next case, we built up a dynamometer testing environment with CarSim RT. On your left-hand side, CarSim RT is used to generate the testing schedule. We use FTP17.5 in this case. CarSim's driver model will send the driver command out to the under testing powertrain system. After receiving the command, the motor will start to generate a torque in order to push the vehicle in a CarSim and also push the dynamometer. CarSim will calculate vehicle speed as a result of the motor torque. This speed is used as a command for the dynamometer. The dynamometer will traction to the under testing motor to fulfill this testing system. Our user tests their motor control unit with this testing system. This can prevent lots of dangerous and costs because we can test it in lab. The last example is the driving simulator. We built this driving simulator with CarSim RT and motion tuning and a 6DOF motion platform. The motion tuning is going to implement the feeling of acceleration on the 6DOF motion platform. Let's say that a real vehicle is running in an infinite world, so that we will always have acceleration, velocities, and position changes. However, the motion platform works in a finite position. Every DOF has a limit. So the question is, how can we use it to generate the result of a real vehicle? We generate with motion tuning. Motion tuning is using to solve this problem. The idea is human cannot sense changes with very low frequency. If the vehicle dynamic changed in very low frequency, motion tuning will use gravity to compensate the feeling and put the motion platform to the origin. That gives space to motion platform for next rapid moving. As you can see, when the vehicle is turning, the motion platform is moving to generate the acceleration of the real car. So here will be brake, turning, and acceleration. And the platform will move back to the origin and wait for the next moving command. Today, we covered 3 topics with some success story. Model-based design is going to help us build the model of our controlled plant. We use a complete vehicle lookup table model from CarSim to build our plant model. With CarSim, we can have a lot of testing procedure. When you want to test with a real controller, you can use hardware in the loop to test it. All of these testing methods can rapidly decrease the cost and the time you need to develop your product. This is all for today. Thank you for your listening. Please leave your question in the chat room and I will start to answer it as soon as possible. Thank you.
Thank you, Jackie. So now it's our Q&A time. If you have any questions, please feel free to type it in the chat window or the Q&A window. Yeah, you can free to ask any questions regarding this presentation.
Okay, here I got a private message about a question. He asked that could we set up the control algorithm in HIL and test with real vehicle? The answer for this question is yes. This kind of method is called model in the loop. We can use it in early stage to make sure our control algorithm meets the requirement. Okay, the next question is there any OEM or supplier use your solutions? CarSim is the most widely used system-level vehicle dynamic simulation software in the automotive industry. And also, CarSim is the company standard vehicle dynamic software in several automotive companies and is in use for various purposes at many more of the world's OEM companies and their suppliers. It is also popular at research labs and universities. So the answer for this question is widely be used globally.
Okay. So are there any questions? Okay, thank you very much. So we don't have any questions now. And thank you for joining today's webinar. I will send you an email with a link to the webinar questionnaire. And please fill in it, and then you'll receive the download link for the webinar file for today. If you have any questions or you want to ask more technical contents about this presentation or anything regarding CarSim, you are also welcomed to contact us through email or phone call. So thank you very much and see you next time. Okay, bye-bye.